just do it this way. Now, when we get vectors with unknown variables, there's lots of different ways to put them in. If I have locations for, now I've done something straight away, instead of calling them X, Y, Z, I've called them X, 1, 2, 3, but I'm not really changing anything. Then I can nominate actual numbers. So I can call the X20 and X30. That's what that actually means when I write it like that. And then I can take X1 out actually. I can take it out like that and multiply it through a vector that's 1, 0, 0. Okay. So what I can do then is I can have some value of lambda that I talked about before equal to 1, and the vector for 1 would be this previous solution, 1, 0, 0. So what I'm just trying to show you is that we can manipulate things quite a lot. So when we set up our matrix equation, what invariably happens, now I'm jumping in here, so I'm going to draw an arrow. I'm being a bit rude here, jumping in. There's a bit of explanation that goes before this line. But if I do this kind of thing, which you may recall, so this is our setup to find our eigenvalue. Okay, so this would be our setup. Now the systems of equations, we jump in. So we're kind of not worrying too much about the whole system of equations, we're just jumping in, which is a little bit rude of me. But if I take my variables, so here's my A, X, B idea. Okay, and I've got my 0 variables, and that's very important because we want them to be AX equals 0. In effect, that's what that means. So that's a big picture metadata matrix algebra type idea. I'll just make that a time so we don't think that it's a dot product. Now if we're given some lambda, the second lambda has the value 4, we're up here, we're given this, then there's a bunch of steps that we've got to go through to get to resolving our values. Now it turns out that when we look at these systems of equations, that we're going to start doing row operations. So the first thing that I would do is target this guy here, but it's already a row, so that's good. This one's already so that's a good one. Okay, the next thing I would want to do is target this one here. Okay, and I would want to continue on then down the line using our row operations. So I'm going to leave that until next week. Okay, all I wanted to do was say, oh, you know what, we set up, this is where we jump in the setup and we start to execute using some particular value. Okay, so in this particular case there's a little bit of row operations. Now it comes in 2 phases. The first phase are all the operations Now ideally we want to get to a place where we can do back substitution, or we could go to a full echelon reduction, one of those. Alright, then the second phase is that once we've got the values of x1, x2 and x3, it's to actually find what those are. Okay. And that's where the eigenvector part comes in. So this is kind of the eigenvalue part, and then the eigenvector. So it's the meta information about what you're doing. So I'm going to press that incomplete and just press pause. Okay, and we'll come back to that next week and we'll have a look at that in terms of operations, because it's quite a lot, and it's something that we can spend a few weeks on because we do have time. But I needed to do this with you because what we're doing is at the harder end of mathematics at university, even for this level. So it's not what some of the professors would say in terms of abstractions, but for us working through it, it's a lot. Okay, so I will walk you through that over the. Well, we've got all of the weeks after STUVAC to get this part out, and it's not that I'm intending to demand of you that you be experts in it, but it's important to me that when I expose you to things, you come away thinking, oh gee, that's doable, you know, and that's why I'm spending so much time going through this stuff this way, so that you come away thinking, you know what, I'm doing a master's in mathematics, what's the matter with me? You know, and I don't mean the teaching one, I mean the one that gets you a job at a bank. Oh, a good question for you. Where do our top engineers go? So engineers come and do an engineering course at UTS, and at the end of their just about to graduate and they've got all the results in, who taps them on the shoulder and where do they go? Any guesses? Have a guess.
Nowadays, probably the tech companies.
Yeah. Anybody? It's the banks. So our top engineering students will get headhunted by the banks. So they've got linear algebra, multivariable calculus. They're in the top 2% now. They're pushing up in the top 2%. They've got programming skills, even civil and mechanical engineers, right? So you can go into a bank room where they've got all their analysts and programmers, and you'll find an array of engineers, civil, electrical, mechanical, environmental. It doesn't matter who they are. It only matters what they did with this stuff. Okay? So it's surprising, but yeah, that's where it goes. So actually one of our professors went to CommBank, and that's along with the bloke who runs FEIT at UTS. That's where that information comes from. Verified, not just a reputational fancy, but it's actually verified by the bloke that left us. So, alright, so that was just an aside. Don't know why I talked about that, but there you go. Okay, so the next thing is that we probably should move on to... Now, one of the things that comes up in the tutorial tonight is that we have a little look at a transformation. Now, this particular transformation from part 1 is actually a rotation. So it actually does do a rotation. Okay, so I'm going to move off onto that now, if that's all right. Did anyone have any other questions, or are we happy to keep going? I've given you a lot. I do give you a lot, don't I? I'm conscious that I give you so much information. That's just like throwing all this stuff at you. Alright, so what I'm going to do is just get them... There's probably enough room to do it on there, I think. No, I think I'll just get them side by side. And... Oh, that's horrific. Okay, and... Can you guys still see that? Leave that one there. Okay, so just shout out if you have any particular questions. So we've got sheet 4. Now, starting with the definition of polar coordinates, x equals r cos theta and y equals r sin theta show the derivatives with respect to r and theta can be written in that form. So basically what that means is that we've got to do what we've been doing with transformation. So I'm going to do it all out for you. So we want to do a transformation with R. So we're going to have our partials with respect to R. So we'll invoke our chain rule, X and R for our chain rule, and so these are partials and these are derivatives. Alright, so for our x is given as r cos theta, so we'll have ddr partial with respect to r for r cos theta, and they're always algebraic, aren't they? Just like the 4-unit topic. The main difference between the extension courses and the advanced course is that they're algebraic. Okay, the next thing is our y is r sine theta. So we're going to do ddr r sine theta and a differential f with respect to y. Alright, so what is the ddr? And this is that silly question, isn't it? There it is. Sorry, I'll move that back up. I actually wanted just to open this one up as a bit of a sidebar. Where's my right here? I'm going to have to open that up a bit further, I think. Sometimes I don't know what happens with things. I use them and then I'm like all of a sudden. I just don't know where that's gone. Go away. Alright, sorry, I'm going to have to do it on here. So this is not necessary to record, it's on the video. So that's alright, sorry about that. And I just turned my video off. I'm having a good night tonight. Where is it? Sorry, I'm going to have to... For some reason I closed it. There you are. Sorry about that. Just scared myself silly. Alright, so I can draw on here. Okay, so this is DDR expression differentiation of r cos theta. So the rule that I've said to you is that if we did a ddx something x, what would be left over? What would be left over if we did a ddx something x? So imagine it was ddx 6x, what would we get after differentiation?
Bit of something?
Yeah, it's just the something, isn't it? So ddx 6x is just 6. Now see that struggle that you're going through now? If you're teaching extension subjects, that's what the students are going through all the time. They're looking at something, they're hearing you say that it's common and you should know it, and they're doing exactly that same blank pulling up. It's not a fault thing, it's not an error, it's just what we do as humans when we're processing stuff. So here, all I'll get after DDR of r cos theta is cos theta. Okay, and because it's a different animal, it's not an x or a y or a 6 or a 9 or what have you, it's just confusing. So when I do DDR of r cos theta and write cos theta, that's what's going on there. Now your students in extension subjects, regardless of whether it's 1 or 2, will experience exactly what you just experienced then, and they'll do it on an ongoing basis. So recognizing that as a teacher is extraordinarily helpful. Okay, because it might just make you pause and think again, do a bit of formative assessment, looking at their faces. If they're really not processing it, then you just do. Now, I've done this a lot with you, haven't I? We've only been together for a month and a bit, and I've done it a lot. And it's repeating and repeating. Sometimes you probably want to chuck something at me, but the point is it goes in, Mrs. Marsh, right? That's a reference to an advertisement for cleaning your teeth from when I was a younger person. All right, you can Google Mrs. Marsh. All right, so it's a Colgate ad. It's Colgating. All right, so this one here, now we know that we've got a bit of experience. What's DDR of r sine theta going to leave us with?
So sine theta.
Yeah, that's right. Just sine theta. Now you've got the hang of it, and that's what students need. They need to get the hang of things. If you brashly say, boom, 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 what's the matter with you? Why you all aren't getting it? I don't love you as a teacher. I'm sorry, but I've been in that class with that teacher, and I can't stay in the class. I have to go. All right, I have to make some lame excuse. Oh, I forgot to be somewhere. I have to go. Okay, so if we don't, and then the problem that you have in ignoring that reality is if you are expecting good results, that might be a problem. All right, so the next part of our building up the chart is we've got our function, now it's theta. So we've got dx d theta, df d theta, this is our total differential, dy d theta, and df dy. That should be an x, I think. That should be an x. Alright, so what do we have for expressions of theta? Okay. So d theta x again, d theta y again, so we get d dx, which will d theta. So now we're doing it with respect to theta for r cos theta. So we're going down the other branch of the tree. Okay, we're going down the branch of the tree for theta. No, that is theta. Why have I changed that? No, I can leave it there. That should be x. Plus d theta for y, which was sine theta. But this time we are doing it down for theta, and we're going function dy. Alright, so now you're pretty practiced with your differentials. If we do the differential of this guy here, what do we get? It's with respect to theta. So it's, so over here it's d theta cos theta. See, because it's algebraic, it's throwing you all. This is what your kids will experience. Okay, if you're doing extension and you write this up, it's so the r's not going anywhere. We did it on the r up here, didn't we? It was all about the r. Up here now it's all about the theta. So for all intents and purposes, this is a constant, and so it will be in the answer. Okay, differential of cos is sine, but it's minus sine. So we'll get minus r sine theta differential x plus, now this one should be r cos theta. Okay, so we can write df dr Now if we take r across the other side for the df d theta, so that again is another little explanation that I'm providing. So if I divide through by r, I'll get 1 on r out the front here. And so on the right hand side you won't get the r term, so we'll get minus sine theta plus cos theta Now we've got our equations, we can do what I did earlier on in the night, which is one of the things that I wanted to do, so this didn't seem like such a big puzzle, and put this into matrix form. So coming into this subject, if you're doing this topic, you've got to remember your algebra from point of view of coefficients. Okay, so if I write this in its form, partial f with partial r, and 1 over r partial f with partial theta, so that's going down that one side of the tree, and then the coefficients that I've got left are cos theta, sine theta, minus sine theta, cos theta. Now look at this, what can you tell me about this bit? What can you tell me about this bit? Just that bit. It's the sum of products. In other words, this is the result of, I know it's a lot, matrix multiplication. Okay? And this is why we're going backwards now. See it over here? That's what they wanted from us. But we had to do this backwards step. Okay? And so much of what you do when you start getting into higher mathematics is this going from one form to another and going backwards in the steps that you've known. It's not new, it's not complicated, but it takes a long time to get comfortable with. So extension will be like that. There'll be times when you're expected to go from one form to another. That's one thing, but there'll be other times when you'll also be expected to go in the reverse procedure. Okay, and it doesn't always present itself so readily. So if that's my transformation matrix, and then my differential is fx and fy. So row down column, but I've swapped them around. See how I put them on the wrong side? I taught it to you like that, but then it's over here it's become on the other side. So it's fine. Alright, so that's a bit of fun. Does anybody want to shoot me yet? I'll just rub this rubbish out. And so what we've managed to do is put it in the form that the question asks for. Now if you think about it, I mean if you really put your 4-unit lens on, that wasn't such a big deal in effectively writing something that we knew about. I did make the point at the time that it's about seeing it in the form of matrix multiplication because it wasn't obvious to you, but now you see it probably is. It's row down column. What does that look like? Row down column. Oh, we've just done row down column, that's easy. Oh, okay, what do they want then? They want us to work through the pre-lines. Here it is, the pre-lines. All of that stuff leads up to row by column. Okay, so that experience that I'm with you tonight here is particularly poignant in my opinion because that's the kind of experience that you have in extension when you're going through particular things that are quite troublesome and quite difficult. It's like the question isn't that abstract, but it required what? Recognition. So if we did this is the result. Oh, this is if we do the row down column, what will we get? We'll get our system of equations that have got these differentials in them. Oh, well, hang on. What do they want us to do? Oh, we've got to work backwards. We've got to start at the very beginning, set up our chain, work through our chain, go down the various parts of the graph, you know, and then X and Y and R and theta, because that's all it was. It wasn't terribly complicated, this one. And work down them that way, okay? And that's what we did. We worked down them, and eventually we got to, ta-da, what they wanted us to do. But gee, there was a lot of rigmarole in the middle, wasn't there? Okay, but remember that as a first encounter, you're always going to feel a bit dusty coming off something like that. That's just the way it is. Any questions, thoughts, comments? You want to throw stuff at me? That's all right. All right. So the next thing we'll do, we'll go on to question 2 because that's a slightly different flavour. Okay. And all I'm trying to do is just get the terrain visible to you. Okay. Get the terrain visible to you. This is not excruciating assessment. Okay. I don't want you to think that. There'll be plenty of opportunities in your life for excruciating assessment. I don't want that for this subject or any of the subjects I teach to teaching stuff. Okay, so we've got a length, width and height of a rectangular box are changing with time. So this is now a very interesting problem, okay, because we're taking a simple geometry, okay, and we're saying that it's on Harry Potter and it's growing or it's shrinking, and so it's got that magicness about it. Okay, I could do all the dotted stuff in the middle if that would be helpful. Okay, I could do all that. So the length and the width and the height of a rectangular, so a box of simple geometry, are changing with time. If the width of the box is decreasing at a rate, okay, of 10 centimeters per second, the height is increasing. Also, they've put some words in here. Now, do you know how I spend the time on the words with you? Your students need that too. My student that I've been working with for a number of years, who I feel is a little bit undercooked in terms of his giftedness, is doing very, very well. And he just sat his trial for advanced maths, but he's in year 11. Okay, so he's coping well. And one of the things I've had to spend time with him is getting these questions out. Be attentive. Now, a few years ago he would have missed the decreasing, increasing. Today he'll pick that up. Okay, what does that mean? If you're 15, 16, you're doing work with you in extension, they're the kinds of things you'll miss. And the length of the boss is decreasing at a rate of 20. Okay, what is the rate of change of the box's volume when the length is 3 meters? Now, a single version of this would be called a related rate. So if you want to remind yourself about related rates, I suggest you go on to the Maths Study Centre website again and go to Resources, Library, Modelling for Science, Worked Examples, Related Rates. Okay, implicit is in the 4-unit syllabus. It's hidden away there, but it is there. Okay, so this is the area of maths that implicit is important for, not just getting the integration tables out. All right, so the volume, we want a volume. In particular, we want dV dt. Now the beauty of this, what I'm trying to do with you people, is entice you, I've used that word, seduce you, to come into the world of mathematics and deal with all kinds of problems. Mechanics, who cares? Physics, who cares? Statistics, who cares? Finances, who cares? This maths, it's the same. It's just that the context is different, the example is different. Okay? So be patient with yourselves and develop your math skills because they're transportable. If you've got a particular pet context that you love, or you might be a bridge builder or a beam stressor or whatever it is that you're interested in, or a finance person, your math is your answer. Be patient and let yourself grow into it. Alright, so what's happening here? So we're going to put the chain rule together, and I want the WDT, so I don't need to use implicit so much here because it's all kind of there. So I'm going to put my partials with respect to volume and W with respect to time. So that's my I'm still going to have the VDT. I'm just going to get it through somewhere else. See, it doesn't go away. Doesn't matter what level of math you're doing, it's still there. In this case here, it's W. Okay, I've had students tell me that until they saw that diagram, they never understood the chain rule. I had a lot of students tell me that, actually. Anyway, apart from that, let's move on. So we've got V, this time we've got L. Plus V height. So we've invoked the chain rule. Okay, the VDW. So dV, dW, or W of WLH. So it's just like it is exactly our partials. So if I'm doing it with respect to W, what would I expect to get left over? L and H are constants, aren't they? If I'm so it's just that one. Okay, if I'm doing it with respect to L, it all looks very foreign when you change it, throwing numerals around, doesn't it? What am I left over with?
The width and the height.
Width and the height. And then the final one is the partial of the height. Okay, so when these disappear, I was going to write the line out. I thought, no, don't do that. So I've just walked you through it. Would have been a big step, wouldn't it, from that line to that line. Now guess what the question's providing us with? These guys. Now that's a big deal in extension subjects. Where's the question info? That is, it's provided. So we've got L equals 3, W equals 2, height equals 4. So that's straight off the question. So then we've got to put it in, and also we've got L is, the length of the box is 20 centimeters per second. So this is just a horrid thing, 20 centimeters per second. Okay, and centimeters as a number is 0.2. So dl dt from the question So the cent is 2, so it gets you to decimals. Centi is 10 to the minus 2, which means you're going 1, 2. Okay, so that's why it's 0.2, 0.1, 0.05. Okay, so dv dt is equal to 3 times 4 plus WH, 2 times 4 is 8, and WL, 2 3s are 6, okay, so not so bad. So we've got, what's that, 10% of 12 negative, we've got 20% of 8, 10% of 8 would be 0.8, so double that's 1.6, but it's negative. I probably wouldn't recommend doing that with students, but they've got to learn to do it. 10% of 6 would be 0.6, and half of that would be 0.3. It's positive. So what have we got? Minus 2.8 minus 2.8 plus 0.3 is minus 2.5 meters cubed second to the minus 1 for the physicists. Remembering that we converted them into meters. So setting that kind of thing aside, it's not too bad. Okay. All right. So I any thoughts about that? It's a lot, isn't it? It's a lot to take in, and it's a lot to process. And if you want to have a look at these chain rules and those kinds of things, do you remember that I put that in as a... Do you remember the location of that? I put that in with a whole bunch of questions that you could look up. Sorry, I'm just coming in as a student, and I don't think it was that. It was in the know-how stuff. Okay, so in the archive drop-in, some worked examples from the examination pool. So if you want to see a whole bunch of worked examples, they're there. Okay, so you can go on the chain rule, and let's just put it there, and I'll open that, and there's a whole bunch of examples. Okay, and you can fiddle with the diagrams, and I mean you don't have to, of course, and I normally I might introduce it in future versions of the subject, but for the time being it's just nice to have there to have a look at, to remind yourself how to pull the chain rule together. And some of them are quite useful in terms of problem solving as you get further down. So there's one. The length L, width W, height of a box change with time at a certain instant. Click on the view solution, and there's your solution. Okay, but I'll leave that for you to peruse at your leisure. This is a very leisurely subject. It's not a subject where we crucify ourselves. Okay, there's enough content. You agree with me? You understand where I'm coming from as a philosophy of teaching this, don't you? There's enough content in this subject for me not to worry you, because I'm being very careful in how I guide you through step by step, because you only got to look left or right, and all of a sudden it's like okay, so the idea is we come away feeling good about what we've done. Alright, so I think what I'll do there is throw it back to you guys. If there's a particular extension type subject question that you wanted me to have a look at, or from the resources I gave you, or some other one, I can either have a go at it now, or I can do it and bring it back to you next time, or send it via email. But you know, I can see a few yawns tonight. Trish, you're looking a bit tired. Forgive me for pointing that out, but you are.
You have had a very big day.
So why don't we just call it time out? All right. Thanks so much, guys. All right. Thanks for coming along, and I will see you next time.
All right. Thanks, Jason.
Thanks,
All right,
Jason.
all the
Thank
best,
you.
guys. Thank you.
See you, Trish. See you, Cindy.
See you later.